Hello and welcome to my video introducing chemistry. Having a basic understanding of chemistry is a good idea if you want to start understanding molecular biology, things like small molecules and enzymes you'll find in cells. And so knowing this sort of stuff is pretty much essential so you can understand what's going on in the future of biology. Alright, so this thing here is the periodic table. You may or may not have seen it. If you have, that's good. If you haven't, that's alright. So pretty much what the periodic table tells you is every atom that we know of, and it tells you in increasing size usually what they are. So an example here is the first element is hydrogen, the smallest element. So hydrogen, you probably heard of it. Hydrogen. My handwriting is very bad. Hydrogen, and it is denoted by an H. Makes sense. Some of them do not make as much sense. So here we have sodium here, Na. So this probably came from another language. And so sodium, you'll hear of sodium a lot in biology. You've probably heard of sodium before. It's half of salt. Okay, so the periodic table will tell you things like this. There's a lot of groups, there's many different kinds of groups. These will be the P block elements, S block elements, but you don't need to know this stuff really unless you're studying chemistry. What I do want you to know though is just keep these in mind. These are the noble gases. Noble gas. And these are important because these have a full outer shell. Full outer shell. Looks like full outer smell. Just because I am not used to this tablet. Okay, so they have a full outer shell. That is important because all elements want to be like the noble gas. They look up to these noble gases. They go, I want to have a full outer shell like them. So what does a full outer shell mean? Let's go down to what makes up an atom. And here I've drawn a basic diagram of what an atom is. In the middle here, we have a nucleus. And surrounding that, we have the orbitals. And in those orbitals are electrons. Those are those purple dots you can see. So the nucleus is here, right there. And those blue lines are the outer shells. Okay, so this red thing here I've drawn, this is just an arbitrary color. These are not actually red, these are protons. Protons. And these have a positive charge. So positive charge. And also paired up with these protons, you have neutrons. Neutrons, not ands, neutrons. You have to forgive me for my handwriting. And just like the name suggests, they have a neutral charge. Neutral. That's a U. Okay, and these smaller purple dots I've drawn are electrons. They are actually much smaller than protons and neutrons. Electrons. And these have a negative charge. And so these electrons are attracted to the positive nucleus, as that keeps them there. And what we have in a neutral atom is we'll have the same amount of protons and electrons. So having the same amount will produce a neutral atom. Neutral atom. If we have more protons or electrons, we have what we call an ion. We'll come to them in a second. So what atoms like to do is they don't like to be alone. They like to pair up or make huge chains, and they achieve this with bonds. So we have a few different kinds of bonds. The ones I'm going to talk about here are not the only bonds you'll find, but these are the ones that you're most likely to find in biology. So a covalent bond is when you're sharing pairs of electrons. So if I was to draw, let's say HCl, hydrochloric acid. So these are just the symbols. And I'm just going to draw dots to represent the electrons. So how many electrons does hydrogen have if it's neutral? Let's have a look. So because it's the first one, we're going to assume that it's also going to have one electron. So it's a neutral atom. And chlorine, over here, will actually have 17 electrons total if it was neutral, but the outer shell So we take it from this row, have 1, 2, 3, 4, 5, 6, 7 valence electrons. We say outer electrons or valence electrons. And only the valence electrons are the ones we're going to find that react. Okay, so let's draw dots to represent these electrons. So we've got one dot there for hydrogen, and how many did chlorine have? It had 7. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. Alright, and so these two electrons are going to be shared between these atoms. This way, they both get an outer shell. So hydrogen is a bit different. When I said that things want an outer shell like the noble gases, they want 8 electrons. It's not true for hydrogen and helium, which have an outer shell of 2. So helium is happy where it is. It doesn't want its electrons taken. Alright. So now that they're sharing electrons, they've both got a sort of fake outer shell of 8. They're both quite happy. And this will be a bond. Now you can have double bonds as well, when you'd have 2 pairs of electrons, so 4 total electrons being shared, or a triple where you'd have 6 total electrons being shared. You can't have a quadruple bond. Don't worry about why, you just can't. Okay, ionic bonds. So when we were talking about ions before, we're going up and we're talking about ions, how something with more or less of electrons and protons will create an ion. They'll have a charge to them. We usually get ionic bonds between this group here, the halogens, and the first block, these red dudes here. This is because these red guys, they have one bonus electron that they don't really want. If they get rid of it, they'll have a full outer shell again. So they're quite happy to get rid of it. And these guys are only 1 away from being like the noble gases. They're super close. They're really, they're like, I want to be like these noble gases. I want to be noble like them. So it's quite happy to just take someone else's electron. So this makes these two groups the perfect pair. So when they come together, let's use table salt, sodium chloride, Na and Cl. So this sodium here, Na, is quite happy to give its electron away. So the electron, let's just say that this is its outer electron, it's going to give it to the chlorine. You can have it. I now have an outer shell. But this is now going to give it a positive charge. So this is the symbol we use to denote positive charges. It's now going to have a positive charge because it's going to have more protons than it does electrons. This chlorine now is going to have a full outer shell, just like the noble gases. Unfortunately, that is also going to make it negatively charged. So we're going to use the symbol to mean negative. And this is going to make an attraction between them two. So they're now attracted to each other. And so they will stick together. These ionic bonds are easy to break with water, so this is why when you chuck in table salt into some water and stir it a bit, you're going to separate these two ions and it's going to dissolve. The last kind of bond, hydrogen, I'll come back to in a second, once we talk about polarity. But first I would just want to talk about the pH scale. So you probably heard of pH before, acids and bases. This is the pH scale. It ranges from 0 to 14 at room temperature. It can actually go either way, above or below, but you don't need to worry about that. Alright, so at 0, we say something is acidic, like lemon juice or hydrochloric acid. And if something's up on the pH scale, I guess, at 14, it is basic. Basic. Look at that B. Basic. Alright, so acids, we say that they are proton donors. They'll give away protons in the form of hydrogen ions. And bases, they're proton acceptors. Acceptors. I think that's an E. Acceptor. Donor. Alright. So the pH scale ranges from 0 to 14. This 7 here I've written in the middle, that is neutral. Neutral. And an example of something that is neutral is pure water. Pure water. That is useful, especially in your body, because it makes you not either acidic or basic, in most cases. Not that that's a bad thing, so slightly acidic things can be good, slightly basic things can be good, and extreme acidic things can be good, such as your stomach, which has a pH in its area about 1 or 2, which is good for digesting food. Alright, the last thing I want to talk about is polarity. So when we have molecules stuck together, such as water, so if I was to use this to represent water, so water looks like that, H2O. 2 hydrogens, 1 oxygen. Alright, H2O. This would be the oxygen, and this would be the hydrogens. What actually happens, as we're talking about before, things want to look like these noble gases, and the oxygen is very desperate to look like these noble gases. So what's going to happen is that the electrons around this hydrogen, the 1 electron around this hydrogen, is going to be more closely found towards this oxygen. And so this oxygen is going to have a negative charge. I want to stress that the oxygen has not stolen the electrons, but they're more likely going to be found around this oxygen. And these hydrogens are going to have a more positive charge. And so this means they have poles, one positive pole and a negative pole. So this is going to be important when it comes to biological systems, because polar things can make a big difference. So this molecule, we would say it is polar. Polar. But we can also have non-polar molecules. Non-polar. Non-polar. An example of a non-polar thing is the oxygen that you breathe, so oxygen gas. So oxygen gas is just 2 oxygens together, and neither of them are more greedy for electrons than the other, and so you actually have a neutral overall charge around them. And so this brings me back to these hydrogen bonds I was talking about. So I'll use green to change things up. So hydrogen bonds happen when you have your water. I'm not going to change the colors to save time. So this is our water, remember, H2O. This is our water. We're going to have the positive charge over this side and the negative charge over this side. And so this means that when we chuck multiple water molecules together, you're going to have the attraction between that positive hydrogen and another oxygen. And so it'll look like that. They're going to be attracted. I'll draw that to mean attraction. And that's going to chain up. There's going to be attraction here between, this is oxygen, oxygen, oxygen. These oxygens are going to be attracted to the hydrogens. And so when you chuck them all together, you're going to get this huge chain of attracted water molecules. So that concludes some basic chemistry you should need to know for, look at that, some basic chemistry that you need to know for biology. We will move on to some simple biochemistry and cell structures soon. I hope you enjoyed this video.